This is my solution for the problem that we did Wednesday. Funny, I almost pronounced it the way it was spelled. Wednesday, week 4. And so we were talking about equivalent capacitance. And so we had a network of capacitors connected by wires. 2 of them were in series, and then those 2 were in parallel with a third. And we said that these were capacitances, and I'm actually just going to write them as C1, C2, and C3, and I'll plug in numbers at the end. So the first thing we want to do is take this network and find out what capacitor would be equivalent to the 2 that are in series. It's usually easiest to add these in pairs, so that's why I'm going to start with those 2. And I'm going to ask myself, what is this capacitance? Where this bottom one is still C3. And how I figure that out is I realize that because these charges are in series, or the capacitors are in series, since they were initially uncharged, once I hook the right plate of one up to the left plate of the other, this whole thing must still be uncharged, this little H on the inside here, which means that the plates for C1 and 2 must have the same charge. So C1 and C2 are in series, so they must have the same charge. If they have the same charge, that must mean that the voltage difference across the network from C1 into the middle to C2, that whole voltage difference is equal to the voltage of the battery. So the whole voltage difference across would be equal to, well, let's see. I know that this is Q over C1 plus Q2 over C2, but they have the same charge, so that's just Q, 1 over C1 plus 1 over C2, which means this thing that's in here must be 1 over C equivalent for these 2. So I'm just going to write that down. So C equivalent, I know what it is now, is 1 over C1 plus 1 over C2. Okay, and now I'm going to go a third step, and I'm going to compare these 2 that are in parallel and make that into just one grand capacitor. And since they're in parallel, and I know that the potential difference between points in the wire, as long as nothing's flowing, has to be 0. In other words, if one end of the wire is held at a certain potential, by the time I get to that plate, it has to be the same potential. So what that means is I can go from this junction to this junction and say that the potential difference across those is just the battery. So what do they have in common? Well, they have the same potential. So C equivalent and C3 are in parallel. So they have the same voltage. Okay, so same voltage. Oh, so if you think about, say, a bunch of positive charges on each of those capacitors, those charges sum together to give you the net charge on our equivalent, or our new equivalent capacitor. So that means that the total charge on the capacitor is Q1 plus Q2, and that's equal to, let's see, so charge is C1 delta V1 plus C2 delta V2. But I know those potentials are the same, those potential differences are the same, the voltages are the same, so I'll just pull it out, delta V, and I get C1 plus C2. So that means that this thing in the parenthesis must be the new C equivalent. And so what I'm going to do is I'm going to find the total C now, this C, is equal to, well, I'm going to add the 2 things. So I'm going to add a 1 over C1 plus 1 over C2. That's the first one. Plus the second one, C3. So now I've added these two. And now I just plug in numbers. So this is 1 over C1 was 3. C2 was 6. And C3 was 2. So 1/3 plus 1/6 is 1/2. I take 1 over that, that's 2. I have another 2. And the answer is 4. And the units were microfarads. And that's the answer.